Good morning, students. This session is for class 12th. Students, we have completed chapter number 6, and that is electromagnetic induction. Now we are ready to solve the exercise given in this chapter. Okay, so let's see. Next question number 6.1, which is shown on the screen. So, in this question, predict the direction of induced current in the situation described by the following figure 6.18 A to F. So you can see here the figures. This one is the A, this figure is B, this one is C, this one is D, this one is E, and this one is F. So in these figures you have to give the direction of the induced current. So students, I hope you know which law is applicable to find out the direction of induced current in a closed circuit. Okay, so in first figure you can see the south pole of this magnet is moving towards the coil. Okay, this one is moving towards the coil. So in this case, if you use Lenge's law, so you will get the direction of induced current in this loop. So what is Lenge's law? I hope you know Lenge's law. So Lenge's law says that the direction of induced current is such that it opposes the cause by which it is produced. So it means the current in this loop induced in such a direction that the here S pole is appear, so that it will repel this S pole of the magnet. Okay, because if this magnet stop its motion, then change in flux through the coil remains 0 and there is no induced current. So to stop this magnet, this phase looks like S pole. So if this one is S pole, so what will be the direction of the current in this loop? So I hope you know this is the direction actually. So you can give your answer like from Q to P, or from Q to P, or P to Q. Okay, so try to write your answer in terms of from Q to P or P to Q. So I hope you understand. Now you can try by yourself. Okay, so this is the hint. I am going to give you complete explanation, but you can try. Now see in the second part, that is in figure B. You can see there are two loops like this, and the magnet is moving toward this one. Suppose this one is loop 1 and this one is second. So the magnet is moving towards loop 1, and S pole of the loop 1 is towards, S pole of the magnet is towards the loop 1. Okay, you can say towards the right face of loop 1, and the north pole of this magnet is moving away from the left face of the loop second. So you should use Lenge's law in this case also. Now this phase must be the current in this loop such that the phase must behave like S pole, because it try to oppose the motion of the magnet, and in this case this phase of the loop must behaves like S pole, so that it can stop this magnet. Okay, if it is north pole, then it will repel this magnet and its motion is increased. So both the right face of the first loop must behaves like south pole, and the left face of the second loop also behaves like a south pole to stop the motion of this magnet, and then there will be no induced current. So by using this law you can find out the direction of the induced current in loop 1 and 2. You can use the direction, or you can use the statements for giving the direction, like from P to Q, or from X to Y, or Y to X, etc. Okay, so you can write the direction of induced current like this. The current in the first coil is from P to Q, or you can say from Q to P. I am not giving the answer, I am telling that how you can write your answers. Okay, so you can write your answers like that, from P to Q in loop 1, or you can say from X to Y or Y to X in loop second. So now let's see the figure C. You can see here, this one is the loop which is connected with a cell, and so it can carry some current in this one. Okay, now when this key is just closed, there must be a current in this circuit. Due to this current, there must be induced current developed in this loop, which does not have any external energy source, that is, there is no battery, but there must be some induced current. Now if current in this loop is clockwise direction, you can see here, so what will the direction of induced current? And you know that induced current develop in such a direction that it can oppose the cause by which it is produced. Now in diagram D or figure D, you can see there is variable current flowing in this circuit, and this is the loop. So if current is variable in this circuit, there must be induced current in this one. So you have to write the directions in these cases. Here you can see there is, this one is the solenoid which contains some battery. So when this is K is tapped, there is current in this solenoid, and due to this current there must be magnetic field. So there is change in magnetic flux through this another loop, and there will be some induced current in this circuit. Similarly, if current is decreasing at a steady rate in this current carrying wire, so there must be some induced current in this loop. So in all these cases, you can use Lenge's law to find out the direction of induced current. So let's see the answer. So you can see answer here. The direction of the induced current in a closed loop is given by the Lenge's law. The given pairs of figures show the direction of induced current when north pole of the bar magnet is moved towards and away from the closed loop respectively. So you can see in this picture, if north pole is moving towards this closed loop, this phase behaves like north pole, and the direction of the current is like this. Okay, and if this north pole is moving away from this current carrying loop, so you can see here the direction of the current in this loop is like this. Okay, because it appears like south pole to stop the motion of the magnet, because the motion of the magnet is caused by which these currents are produced in these loops. So since north pole is moving towards the coil, the phase behaves like north pole to repel this magnet, and when it is moving away, then it behaves like south pole to attract, and so that it can stop the magnet. So this is the reason, or this is the law known as Lenz law, by which you can give the directions of the current in different loops. So in first case, you can see, so if it is moving toward this magnet, this behaves like a south pole. Okay, so in this case, current is moving like this in this direction. So this is the direction from Q to P, or you can say this is like this one. So from Q to P and then R to Q. So this is the direction of induced current in this circuit. Okay, now I hope you understand what is the direction of current in this circuit. In that case, there is again south pole, and this one is the north pole. So direction of current in this part is like this. PRQP, you can see here. P to R, then Q to P. So this is the direction of the induced current. Here this direction is like north pole, so this one is like YZXY, you can see. Okay, now in figure D, the direction of induced current is along ZYXZ. So you can see here in D, this is like this one. Okay, to oppose the current, sorry, to oppose the cause by which this current is produced. So this is like ZYXZ. Now you can see the direction of induced current is along X or YX. By using Lenge's law, if this is the direction of the magnetic field, this try to oppose. Okay, and now in this case, no current is induced since field lines are lying in the plane of the closed loop. So you can see here in this case there is no induced current because the field lines are lying in the plane of the closed loop. So in this case there is no current induced in this circuit. Now question number 6.2. Use Lenge's law to determine the direction of induced current in the situations described in the figure. So first one is a wire is irregular shape turning into a circular shape. So you can see this is the wire of irregular shape and this is turning into the circular shape. Then what will be the direction of the induced current? Second, a circular loop being deformed into a narrow straight wire. Now a circular loop is being deformed into a narrow straight wire. So let's see the answer. As the loop changes from irregular shape to circular shape, its area increases, hence the magnetic flux linked with the increases. According to Lenge's law, the induced current should be produced magnetic field in the opposite direction of the original flux. So for this, induced current should be flow in the anti-clockwise direction. It means the direction of current will be along the A, B, C, D, A. So you can see here the direction A, B, A, D, C, B, A, D, C, B, A. This is the direction, that is anti-clockwise direction. Okay. And in the figure B you can see a circular wire being deformed into a narrow straight wire. So as circular loop is being deformed into a narrow straight wire, its area decreases and the magnetic field linked with it also decreases. And by Lenge's law, induced current should be produced a flux in the direction of original flux. For this, the induced current should be flow in anti-clockwise direction. It means the direction of current will be ADCB. So you can see this is the direction in this case, and because this is the direction of the induced current, so it opposes the cause by which it is produced. Okay, so these are the directions of current in these two cases. Let's see the question 6.3. A long solenoid with 15 turns per centimeter has a small loop of area 2 cm square placed inside the solenoid normal to its axis. If current carried by the solenoid changes steadily from 2 ampere to 4 ampere in 0.1 seconds, what is the induced EMF in the loop while the current is changing? So you can see here what are the given quantities actually. So you can see the solenoid with 15 turns per centimeter, the number of turns per centimeter is given, that is small n is given here. Then the small loop of area 2 cm square placed inside the solenoid. There is another loop which is placed inside this solenoid, that has area of cross section is area 2 cm square, and current in the solenoid is changing from 2 to 4 ampere it means rate of change of current is given here, and if you use that is this change is 20 per second. Okay, then what is the induced EMF of the loop? So let's see what are the given quantities. So you can see here number of turns on the solenoid is given 15 turns per centimeter. It means per meter it is 1500. We are using them all the quantities in MKS system, so we must convert this centimeter into meter. Okay, so number of turns per unit length is given by 1500, that is small n. The solenoid has a small loop of area A is equal to 2 centimeter square. It means the area in MKS system is 2 into 10 to the power minus 4 meter square. This is centimeter, this one is in meter. Current carried by solenoid changes from 2 ampere to 4 ampere. So change in current in the solenoid is, that is di is equal to 2 ampere. And the time of this change, that is time interval, is 0.1 second. So induced EMF in the solenoid is given by the Faraday's law, that is E is equal to d phi by dt. This is the Faraday law by which the induced EMF is given in the closed circuit. Now you can replace this phi by B into A. So where phi is the induced flux through the small loop, and you can write B into A. So for solenoid, B is given by, the magnetic field is given by mu naught Ni. This is the magnetic field due to solenoid, where mu naught is the permeability of the free space, and its value is given by 4 pi into 10 to the power minus 7 Henry per meter, and the value of N is given 1500 turns, and this value of I is not given here, so we will change this I into di by dt. So let us use these values in this equation, that is equation number 1. So we can replace this phi by B into A. So you can write E is equal to d phi by dt into B into A. Now since A is constant, and in this equation mu naught and N is also constant, so you can write A mu naught into N into di by dt. This is the variable quantity. Now you can replace the value of A by the given value, that is 2 into 10 to the power minus 4. So you can use this value at the place of A, then value of mu naught at the place of mu naught, value of N at the place of N, and then the rate of change of current, that is 2 by 0.1. So the final answer will be, after calculation you will get 7.54 into 10 to the power minus 6 volt. This is the value of EMF induced in this loop. Okay, now next question, that is 6.4. A rectangular wire loop of side 8 centimeter and 2 centimeters. You can see this one is the rectangle, so its sides are 8 centimeter and 2 centimeter, with a small cut, is moving out of a region of uniform magnetic field of magnitude 0.3 Tesla, directed normal to the loop. Okay, what is the EMF developed across the cut if the velocity of the loop is 1 centimeter per second in the direction normal to the longer side, then shorter side of the loop? For how long does the induced voltage last in each case? Okay, so you know that this one is the rectangular loop, and it is moving in a perpendicular magnetic field with a velocity that is 1 centimeter per second. So let us write the given quantities first. So length of the rectangular wire is L is equal to 8 centimeter, that is 0.08 meter. We are changing this CGS system into MKS. Okay, now width of the rectangular wire is B is equal to 2 centimeter, means 0.02 meter. Hence area of the rectangular loop is A is equal to L into B. So the total area of the rectangular loop will be 16 into 10 to the power minus 4 meter square. And the magnetic field strength is given, that is 0.3 Tesla. Now the velocity of the loop is V is equal to 1 centimeter per second, that will be 0.01 meter per second, right? So the first case is when it is moving normal to the longer side. So if it is moving normal to the longer side, then in that case the EMF developed in the loop is given by the formula, that is E is equal to BLV. Okay, in this case the length is taken as the length of the longer side because it is direction normal to the longer side. So in this case the length is taken as 0.08. So the total induced EMF in this rectangular loop is 2.4 into 10 to the power minus 4 volt. Students, we have already derived this formula, so we are here continuously using this formula for when a conducting rod moving in magnetic field. So the EMF induced along at the ends of the rod is given by B is equal to E is equal to B, that is magnetic field, L that is length, and V is velocity. Okay, now the time taken, so you can find out the time taken. So time taken to travel along this distance is T. So distance is distance traveled by B, because this B is L is, because you can see this side is perpendicular. Okay, so you must use this much side, that is the width of the loop. So distance traveled by B upon V. So B is equal to 0.02 and the velocity is 0.01. So it took 2 seconds, or you can say it takes 2 seconds to move from the magnetic field. Okay, and develop so the induced EMF lasts in time 2 seconds, because it will be out from the magnetic field after 2 seconds. So there will be the induced voltage for this time interval 2 seconds. Okay, now in the second case the formula is same but the side is changed now. So the length of the loop becomes the width of the loop, and that is 0.02. Other quantities are remain same, that is B is same and velocity of the loop remains same. So the EMF induced in this loop is given by 0.6 into 10 to the power minus 4 volt. But in this case it takes some more time, because distance of the length of the rectangular loop is quite large. So you can see the distance travel upon velocity, and distance in this case is the length of the loop. So it is 0.08 by 0.01, that is 8 seconds. So hence in this case the induced voltage is 0.6 into 10 to the power minus 4 volt, and which lasts for 8 seconds. Okay, so student, I hope you understand. Suppose this is the magnetic field. If you can draw the magnetic field, this is the perpendicular and inward plane of paper, and this one is the rectangular loop. Okay, so suppose this is the side, that is AB, this side AB, and the loop is moving in this direction. So length in this case is taken as this one, okay, and this is the length, means this is the distance for which it traveled to reach out from this magnetic field. And if you change the orientation by 90°, this becomes the length for which it traveled to move outside this magnetic field, and this one becomes the length of the loop. So this concept is using here to find out the induced EMF and the time taken to travel along the length. Okay, so I hope you understand this concept. Let's see the next question, that is question number 6.5. A 1 meter long metallic rod is rotated with an angular frequency, or you can see angular velocity, that is 400 radian per second, about an axis normal to the rod, passing through its one end. Okay, the other end of the rod is in contact with the circular metallic ring A constant and uniform magnetic field of 0.5 Tesla parallel to the axis exists everywhere. So calculate the EMF developed between the center and the ring. Okay, so you can see the condition is like this. This one is the condition. This is fixed here and it is rotating like this. Okay. This one is actually rotating on a circular track. So you can see, let me repeat the question. A 1 meter long metallic rod, it means its length is taken as 1 meter. A 1 meter long metallic rod is rotated with an angular velocity of 400 radian per second about an axis normal to the rod. So axis of rotation is perpendicular to the plane of paper and inward and outward. Okay, so about an axis normal to the rod passing through its one of the end. So let this one is the end from where this axis is passing. The other end of the rod is contact with the circular metallic ring. This end is contact with the circular metallic ring. A constant uniform magnetic field of 0.5 Tesla parallel to axis and exists everywhere. So calculate the EMF developed between the center and the ring. So let's see. The given quantities are length of the rod is 1 meter, then angular frequency is 400 radian per second, magnetic field strength is 0.5 Tesla. One end of the rod has zero linear velocity while the other has the linear velocity, that is L into omega. Since in this case the radius is taken as 1 meter, so we know that V is equal to R omega, R into omega. So here R is equal to 1 and into omega. So V becomes equal to omega. Okay, so this is 1 into omega. Now average linear velocity of the rod V becomes L omega plus 0 by 2. This is the average linear velocity because one of the end has the velocity L into omega where L is equal to 1 meter and second end is 0. So the average velocity becomes L omega by 2. Now EMF developed between the center and the ring is given by E is equal to BLV. This is the formula for this case. So if we use B then into L, then the value of V, that is L omega by 2. So you can use the formula B then L square omega by 2. Now since the value of L is 1 and B is 0.5, you can substitute the values of all the variables given in the question and you will get the answer, that is 100 volt. So hence the EMF developed between the center and the ring is 100 volts. So this is the answer of this question. So student, I hope you understand how this question is solved. This formula is very important. Remember this formula for the case when a rod is rotating in perpendicular magnetic field. So you can direct apply the formula, that is B L square omega by 2. Why this is? Because this is the actual formula, that is E is equal to BLV. Now at the place of V you can use L omega by 2 because the average velocity of the rod is L omega by 2. Okay, this is the average velocity of the rod. So in this formula you have to use this value of V, that is L omega by 2, and after using this value you will get the formula B L square omega by 2, where B is the strength of the magnetic field, L is length of the rod or you can say radius of the circular track, and omega is the angular frequency or you can say angular velocity of the rod divided by 2. So after substituting the values which are given in the question, you can see here the value of B is 0.5 Tesla, value of L, that is 1 meter, the value of omega, that is 400, and upon 2. This will give you the answer of this question, that is 100 volt. So students, I hope you understand these questions which are explained here. We will solve question number 6.6 in our next session and other questions given in this exercise. So before starting the next session, you should try to solve questions by try to solve these questions by yourself. Okay, so you will be able to understand the concept in more deep way. Thank you for watching this session.